Hi everyone, in today's video we're going to talk about the normal distribution as a continuation of the previous video where I introduced probability, random variables, and probability distributions. If these ideas still sound unfamiliar to you, please watch or rewatch this earlier video. So now let's get into it. This video will cover the normal distribution, standardization and Z scores, skewness, excess kurtosis, and modality. As a quick reminder, a probability distribution is just a tool that helps us understand how likely specific events or phenomena are to happen or to be observed in nature. And there are two main types of distributions: discrete distributions and continuous distributions. Discrete distributions are usually represented with a bar chart, and continuous distributions are either represented with a curve or a histogram. It turns out that the normal distribution is a continuous distribution, and if you don't know the difference between discrete and continuous distributions, watch my video on probability and probability distributions. So why is the normal distribution so important in data science and machine learning? One of the main reasons is that many natural phenomena follow a normal distribution. For example, the height of trees in a forest or even the diameter of their trunks tend to approximate a normal distribution. Also, if you walk to work regularly and keep track of your commute time, let's say a few dozen times, then the random variable representing travel time will end up following a normal distribution, with most commute times centered around the average. Some commute times will be way shorter than average, perhaps because on these days you woke up late and had to walk faster than usual. And some commute times will be way longer than average. Now let's see what the shape of the normal distribution, which is also called the Gaussian distribution, looks like. It looks like this. It looks like a bell curve, and it's called a bell curve, by the way. And this shape is defined by two parameters: the mean, denoted mu, and the standard deviation, denoted sigma. This shape can change if we change these parameters. For example, if we decrease sigma, the standard deviation, then the distribution may become taller as well as thinner in the center and have thinner tails as well. Note that the normal distribution is perfectly symmetrical about the mean, which implies that 50% of data will be greater than the mean and the other half are going to be smaller than average. Another characteristic of the normal distribution is that approximately 68% of data lies between -1 and +1 standard deviations from the mean. Approximately 95% of data lies between -2 and +2 standard deviations from the mean. And approximately 99.7% of data lies between -3 and +3 standard deviations from the mean. And this property of the normal distribution makes estimating probabilities and performing statistical tests super easy. And when I say statistical tests, I'm thinking about building confidence intervals and performing hypothesis testing. Now let's take a real-world example: IQ scores. IQ scores are approximately normally distributed. So let's pretend that this is the distribution of IQ scores. We have a mean of 100, a standard deviation of 15, and we're going to use the properties of the normal distribution to estimate the probability of observing someone with a specific IQ score. If you recall what I said earlier, there's a 68% probability of observing someone with an IQ score between 85 and 115. There's a 95% probability of observing someone with an IQ score between 70 and 130, and a 99.7% probability of observing someone with an IQ score between 55 and 145. And from this, we can also infer that the probability of someone having an IQ score less than 70, so in this area, is 2.5%, and the probability of observing someone with an IQ score above 130, so in this area, is also 2.5, since we have 95% of people falling between 70 and 130, and since the distribution is symmetrical, the remaining 5% are split between the two tails. We're going to find 2.5% in the left tail and 2.5% in the right tail. Now, what if we want to find the probability that someone has an IQ score less than 80 or greater than 135? Well, we could use the CDF of the normal distribution, which looks like this. But instead, we're going to standardize our data so as to turn this distribution into a standard normal distribution. Standardizing data means that we're going to turn each value of x, each value in our dataset, into a z-score so that the original distribution has a mean of 0 and a standard deviation of 1. Currently, the mean is equal to 100 and the standard deviation is 15. And to turn each value of x into a z-score, we're going to subtract the mean from this particular value of x, and we're going to divide the difference by the standard deviation, which is 15. So let's say we want to compute the z-score for a particular IQ score. Here on the x-axis we have IQ scores. So let's say we want to compute the z-score of this IQ score, which is 80. Well, we're going to subtract the mean from 80, which is going to give us a negative value, a negative 20, which we're going to divide by the standard deviation, which is 15. And that's going to give us a z-score of minus 1.33. And the z-score is just a measure that tells you how many standard deviations this particular value of x is away from the mean. So here, this IQ score is minus 1.33 standard deviations away from the mean. And let's say someone who has an IQ score of 135 would be 2.33 standard deviations above the mean, so away from the mean, but to the right in the distribution. And if we want to compute the probability that someone has an IQ score less than 80 or above 135, we can now use the Z tables because our original distribution has been turned into a standard normal distribution, and we can use the Z tables. The Z tables can be found online. Just type standard normal distribution Z table into a search engine. You're going to get a bunch of results. Just pick one of them. Let's go to ztable.com. On this website, you're going to find two Z tables, one that shows probabilities associated with negative Z scores, and a second Z table that shows probabilities associated with positive Z scores. In our example, the first Z score was negative 1.33. So we need to look at the first column, at column Z, and scroll down all the way to row negative 1.3. The other columns represent the second digit after the decimal point. In our case, the second digit is 3. So we need to look at column 0.03. And we find at the intersection between this column and row negative 1.3, the probability of observing someone who has an IQ score less than 80. So it's a 0.0918 probability, in other words, a 9.18% probability. And the second Z-score in our example, which was associated with an IQ score of 135, is 2.33. So we need to switch tables and go to the Z table that shows probabilities associated with positive Z-scores. Again, we go to column Z and we scroll down all the way to the Z-score we are looking for. Here it's row 2.3. And again, the second digit after the decimal point is 3, so we need to look at column 0.03. And at the intersection between this column and row 2.3, we find the probability of observing someone who has an IQ score less than 135, but we wanted to find the probability of encountering someone who has an IQ score greater than this value. So we need to subtract this probability from 1. 1 minus 0.9901 gives you a very small probability. It's a 0.1% probability of encountering someone with such a high IQ score. We can also compute these same probabilities using Python code. So the first step consists of importing the Scipy stats norm package. So let's execute this cell. Then we define the distribution parameters. So the mean is 100 and the standard deviation is 15. To compute the probability of observing someone with an IQ score less than 80, we don't need to find the z-score associated with this IQ score. The norm.cdf function is going to take care of all the work for us. We just need to pass the IQ score 80, the mean, and the standard deviation to the norm.cdf function, which is going to return a probability of 0.0912, which is the same we found when we used the Z table, remember. And the probability of encountering someone who's very smart, who has an IQ score greater than 135, is going to be computed using the same process. So first, we're going to find the probability of running into someone who has an IQ less than 135. So again, we use the norm.cdf function. We pass the IQ score, 135, the mean, the standard deviation, and this is going to return a very high probability, 0.9901, which is, again, the same we found when we used the Z tables. And therefore, the probability of encountering someone who has an IQ higher than 135 is 1 minus the probability of encountering someone who has an IQ less than 135, and that's a probability of 0.0098. In other words, it's approximately a 0.1% probability. So we've seen what the normal distribution looks like and how to use it, especially how to use the standard normal distribution and the z-tables to find probabilities. We've also seen that the normal distribution is perfectly symmetrical, which makes it very handy to find probabilities. But in real-world data, we're going to rarely find random variables that are perfectly normally distributed and therefore perfectly symmetrical. And a random variable that's not perfectly symmetrical is said to be asymmetrical. So is there a way to assess how asymmetrical a random variable distribution is? And the answer is yes. It's called skewness. So let's talk about it. I'm not going to bother displaying the formula to compute the skewness coefficient. Just know that you can use Python libraries such as pandas or Scipy, which come with built-in functions to compute this coefficient. What you must remember, though, is the following. When you have a normal distribution, the general rule of thumb says that the mean is equal to the median, which is equal to the mode. So mean, median, and mode are the same. They fall at the same point in the center of the distribution, and the skewness is equal to 0. Keep in mind that the skewness coefficient is a measure of asymmetry, which is the contrary of symmetry. So a skewness of 0 says that the distribution is perfectly symmetrical, whereas a positive or a negative skewness means that your distribution is asymmetrical. Sometimes you'll come across left skewed distributions with a stretched and thick left tail where the likelihood of finding very small values of x is higher than the likelihood of finding very large values of x. You can see that the right tail is almost non-existent. And since there are many very small values of x and very few large values of x, the mean is less than the median, which in turn is less than the mode. And the skewness here in this case is negative. So this is a entirely made up value, but when you have a left skewed distribution, the skewness is negative. And sometimes you'll come across right skewed distributions with thick and very stretched right tails, where the likelihood of finding very large values of x is higher than the likelihood of finding very small values of x. Here it's the left tail that is almost non-existent. And since there are many very large values of x and very few small values of x, or very small values of x, the mean is going to be greater than the median, which in turn is greater than the mode. In this case, the skewness is positive. So whenever you have a right skewed distribution, the skewness is positive. And note that the skewness coefficient ranges between minus infinity to positive infinity. The skewness coefficient doesn't tell you whether the distribution is normal or not. It tells you if it is symmetrical or asymmetrical. But when you combine skewness with excess kurtosis, you get a more detailed picture of what the distribution looks like. Let's talk about excess kurtosis. The excess kurtosis coefficient tells you how tall or how short a distribution is versus the normal distribution, and more importantly, it describes the thickness of the tails of this particular distribution. The normal distribution has an excess kurtosis of 0, and it is said to be mesokurtic, whereas a distribution that has a positive excess kurtosis, so let's say 5, is taller than normal and has thicker or fatter tails. And this type of distribution is said to be leptokurtic. Finally, some distributions have negative excess kurtosis and are shorter than normal with thinner tails than those of a normal distribution. And these distributions are said to be platykurtic. Note that the excess kurtosis coefficient ranges from -2 to positive infinity, and it can be computed using Scipy or pandas, among others. Now, suppose you want to compute the skewness and kurtosis of a particular distribution without even looking at it. If both skewness and kurtosis are very close to 0, that alone doesn't guarantee you that your distribution is normal, but you can tell that it resembles a normal distribution in terms of symmetry and tail thickness. In order to formally attest that the distribution is normal, you need additional checks, such as visualizing it with a histogram, a curve, or a QQ plot, or even performing a normality test such as the Kolmogorov-Smirnov test, among other existing normality tests. And finally, let's make a quick detour to talk about modality. Modality refers to the number of peaks you see when you observe a probability distribution. The normal distribution is said to be unimodal because there's only one peak at the center of the distribution. For example, when taken individually, the distribution of heights of 1,000 adult females approximates a normal distribution and is unimodal. But sometimes distributions have two peaks and are called bimodal. A bimodal distribution is oftentimes the result of a mixture of two distinct distributions or two distinct populations. If you mix up the heights of 1,000 adult females and the heights of 1,000 adult males, and you visualize the resulting distribution, it's going to look bimodal. It's going to have two peaks because the average height of women is slightly lower than the average height of men. Likewise, if you mix up three distinct distributions, say the heights of 1,000 children, the heights of 1,000 adult females, and the heights of 1,000 adult males, you're going to get a trimodal distribution, a distribution with three peaks. By the way, any distribution that has more than one peak is called a multimodal distribution. Therefore, a bimodal or a trimodal distribution is a multimodal distribution. I guess that's the end of this video. If you enjoyed it, please subscribe, share, like, comment. Thanks for watching and see you next time.